Hi everybody, another BMED 3300 biotransport lecture for you, this time on the substantive derivative. This is part of the introductory section of the notes towards the end. If you are not familiar with partial derivatives, the dot product, and the gradient operator, I strongly suggest you stop listening to this lecture now and go back and listen to the math preliminaries lecture that I did earlier, because you need that mathematical background information to understand what we're going to talk about today. Okay, so what is the substantive derivative? And to show this, we're going to consider this contraction here. So this is taken from the notes. And I would like you to think about a small fluid particle. Let's just draw it in like that. And you notice that there's a flow from left to right here, as shown by the arrow. And we're going to suppose that that particle has some quantity g associated with it. So g could be the temperature of the particle, it could be the concentration of some substance in that particle, it could be density, it could be a whole bunch of things. It's extremely general. And we ask the question, how does g change with time? What is dg dt? But we ask it in a very specific way, because we're going to do what we call material following. And what that means is that as this flow goes from left to right, this particle is going to go along some kind of a trajectory, and so at some time later it's going to be over here, and then it's going to be here, etc., etc. And we are going to follow that little particle along. So this is very much a Lagrangian type of approach, where we're actually following a fixed collection of matter, which is this particle, and asking how that quantity g changes for that particle. Okay, well, that seems not too hard, so let's just think about that a little bit more. We know that g is going to depend on the position of the particle, so let's define some quantity x here, like this. So we know that g is going to depend on x, and in general x will be a vector, but to keep the math simple, we're just going to leave it as a scalar. So we'll just worry about traveling left to right for purposes of this derivation. But the quantity g could also depend on time. So let's make this a little bit more specific now. Suppose that there were some cells on the wall of this converging channel. So I'm showing those by those little bumps here. And let's suppose that those cells are secreting some kind of a substance. Let's say it's a growth factor. So this could be a bioreactor or something like that. And let's make g be the concentration of that growth factor inside that little fluid particle. Well, obviously, as the fluid particle travels along, it's going to have its concentration of that growth factor increase with time. But then suppose I also did something to these cells by administering some kind of a cytokine to them to make them secrete more growth factor. Then you would have a situation where things are changing with time. And so this is what this notation here represents. This tells us that g can change with time, and that, by the way, represents the unsteadiness, because if you think back, our definition of steady was that nothing changed with time. But this also shows that g can change with x position. So now there's kind of a nasty thing here, though, and I want you to remember that we talked about this as being something called material following. So actually x is the position of this little particle, and you can see that x itself depends on time t. So it's like time shows up twice here. It's hidden inside x, and then it's more explicitly in this second position here. And it's this dg dt that we need to calculate here. So how are we going to do that? Now let's switch to another page. So I'll just remind you that we're going to have g which depends on x and t, and we want to calculate dg dt. But we're going to do that in this special material following way. And so we actually have a special symbol for that in transport, which is big D G dt. And you'll sometimes see this called the substantive derivative. And it means that you're actually following a little substance or a chunk of fluid. So to be able to do this, I need to remind you of something called the chain rule. And what does the chain rule says? It says, suppose I have a function f, which depends on a function g, which in turn depends on a variable t. So for example, I could have something like sine of x squared, or let's make this t squared here. Right? So t squared is a function, and that plays the role of g, and then sine is a function, and that plays the role of f. And we ask the question, what happens, or how do I compute the derivative of that? Well, I hope you all remember that to compute this derivative, I have to first of all do df dg, and then I have to multiply that by dg dt. So in the case of my sine, f is sine of t squared, so d, and we're going to say that, so f is sine of g, and g is t squared, so that this derivative here is going to be cosine of t squared, right? That's what I get when I differentiate sine with respect to its argument. And then if I differentiate t squared with respect to t, I get 2t, right? And that's what we've written up here. So we're going to need that, and it's a little bit messy, sorry about that, but it's a little bit of mathematical background for you. So let's come back to this substantive derivative. I want to know what is dg dt, where I explicitly account for the fact that g depends on x of t and on time explicitly. Now, you can see that I'm kind of going to have to differentiate this twice, because obviously I'm going to have to differentiate this function with respect to this t here. That's not too complicated, although I have to use a partial derivative to do that. But I also have to differentiate it with respect to this x here, because x depends on t, and so this is where our chain rule is going to come in. And the total change of g with respect to time is going to be the sum of the partial derivatives that I get when I do the second, or derivative with respect to this t, and the derivative with respect to this t. So let's write that out in math. And that's complicated, by the way. So I have here dg dx times dx dt. So that's chain rule. And then I have dg dt partial derivative. And just to be 100% clear about this, this term here comes from differentiating that t there, and this term here comes from using the chain rule on that term there. Now, let's look at this dx dt term, or partial x partial t term here. Remember that x is the position of the fluid particle. So dx dt is just the rate of change of position of that fluid particle. And what's that? Well, that's just equal to the x component of the velocity of that fluid particle. So if I make that substitution, I can write this as bx partial g with respect to x plus partial g with respect to t. And that is the substantive derivative. So it's kind of weird. It has two terms in it. One tells you how things are explicitly changing with time, and the other one accounts for the fact that the particle is moving, and so even though everything is steady, you could still have g changing for that fluid particle. Now, I mentioned before that in more complicated flows, g is going to depend on x, but now x could be a vector. Before it was just a scalar. And so I need to just quickly tell you, how do we do d by dt of that more complicated thing? Well, it turns out it's actually not bad, because what I'm going to do is I'm going to write g in terms of its scalar dependencies. Remember, x vector can be written as xyz scalar. So what we're saying here is that g depends on x scalar, which is a function of time, y scalar, which is a function of time, z scalar, and then explicitly on t. But no problem, I just do the same thing with chain rule over again. So I'm going to have dg dx times partial x partial t, dg dy, or partial g partial y with respect to partial y partial t. So that's a y and that's a g there. dg dz times partial z with respect to t plus dg dt. And then just like before, I immediately recognize that this guy is v sub x, this guy is v sub y, this guy is v sub z. Remember, I have three components of my velocity vector v. And so at the end of it all, I just end up with vx dg dx plus vy dg dy plus vz dg dz plus dg dt. And this part here is kind of hard to write out because there's a lot of terms. So we can abbreviate that by writing v vector dot product gradient of g. And here's where you need to know what dot product and gradient mean from the math lecture that I referred to earlier, plus dg dt. And that is the substantive derivative of the quantity g with respect to time. And if we go back to the notes and look down in the notes, you will see that, oops, excuse me, going the wrong direction here. You will see that we have derived exactly what is shown in the notes. Seem to be having a hard time finding it here. So what we just derived is this yellow highlighted equation. And I am going to ask you to remember that because we do need to use it a couple times during the term. And specifically, we can use that to calculate the acceleration of a fluid particle, which is real important when it comes time to do F equals ma. So that's the substantive derivative. Thanks for listening.